Hey folks, let's talk about changes in equilibrium, also known as Le Chatelier's principle. What it means is basically when you change an equilibrium reaction, it shifts direction to return the reaction to equilibrium. And my favorite way to think about it is what's actually happening inside the reaction. The kind of changes I'm talking about are partial pressure changes, so that's adding or subtracting amounts of gas that are reacting in the reaction, or if it's a reaction in solution, changing the concentration of things that are dissolved in the liquid. Okay. If it's just a solid or a liquid, they hardly change the equilibrium, so that usually doesn't affect the reaction. But if it's stuff dissolved, then they can hit and combine and react. The temperature or the pressure of the system. So let me show you how. There's this one reaction, it's pretty cool, it's this cobalt chloride compound in water, and it's blue when you just dissolve it. What's interesting is that if you could shift the reaction this way, it turns pink because it creates a complex of cobalt chloride in water. I was trying to find the details on it. It's hard to know, and the details aren't very clear, but they do know that it sticks together and it forms pink, it breaks apart, it forms blue. The reaction is also exothermic, so it gives off heat. So, think about it. So what's really fun is that you can actually shift the direction of the reaction and cause it to go from blue to pink, depending on a few different things. Okay, all right. First thing first, the delta H is negative. So what you can do is you actually can kind of think of heat as a product. Okay, so this gives off heat, and this side is a negative. If it was endothermic, you would be taking in heat plus heat, like this, but it's not. It's this. And the reaction is these two coming together and then making this new thing here. And this is what we have here. So we have things combining to form this. Okay, so if we could get the reaction going this way, it'll go this way. If we go this way, it'll go that way. What does that mean? You'll see. Well, we have aqueous. Actually, this is liquid, but they do interact with each other, and aqueous and heat. Okay. If I add more of this cobalt chloride, I have a lot of substances all of a sudden. They start combining with water, and the reaction goes that way. That kind of makes sense, right? Same thing if I add water in this particular reaction. You can actually drive the reaction that way, which is pretty cool. Awesome. If you say you add more of this cobalt chloride hexahydrate to it, you can actually drive the reaction that way. That's pretty great. You could also, if you wanted to, remove water, remove H2O, and the reaction will go that way, because really it's a battle of two reactions, one going this way and one going this way. If you remove water, this one goes slower in this direction, but this one is still going in this direction here, so it moves this way. And really that's the best way to think about these reactions, in that it's a competition between this reaction and this reaction. And if you give an edge to any of these sides, they win until equilibrium is established. Okay. Next thing, what happens if you take away some of this? So say this, you pull some out. Well, this reaction, there's less of a reaction going this way, but this is still happening, so the reaction shifts to the right. What's really interesting is that for exothermic reactions, if you add heat, you think it would speed up the reaction, but heat is kind of like a product, and it pushes this reaction this way, so the reaction shifts to the left, and it goes from pink to blue. Alternatively, say it's blue and you take away heat, you cool it down, this reaction shifts this way, mainly because this reaction is slowed down and this one wins. So this is Le Chatelier's principle, folks. The reaction kind of like reacts according to balance. So you can think of it sometimes like a reaction where you add more stuff here, the water goes downhill this way. If you add it here, it goes down this way. If you subtract here, the reaction goes this way. Subtract here, the reaction goes that way. So the reaction just kind of solves itself depending on the ratios it wants to make. The final piece of the puzzle is compression and decompression. And that changes the reaction when you have different number of gas particles on each side. So for instance, this one here, this is N2O4, this is NO2. This is a dark brown reddish color. This is like a clearish color, like a yellow actually. Okay. All right. So regular, say you have a ratio equilibrium of this to this, okay, it's pretty good. If you compress it, there's more collisions here, right? Because we have two of these to one of these. They collide and the reaction goes this way. So the reaction shifts, so it goes from red to clear. If you increase the volume, the pressure goes down, less collisions, right? Then the reaction shifts this way because this reaction is less because there's less collisions and goes that way. Right? Pretty cool, huh? So usually it kind of, when you add pressure, it moves in the direction of the least number of moles. It goes from 2 to 1. That's kind of a min-max. But really just think about it. Because if you have the same number of moles of gas on each side, changing volume and changing the pressure of something doesn't really do anything. So I have two HI molecules given to H2 and I2. So 2 of these and 2 of these. This is at equilibrium. Okay, all right. If I decrease the volume here, sure, these collide more, and this actually, you see the air gets bigger, it goes faster this way, but so does this. These collide more and they go faster this way, and they kind of cancel each other out. The truth is they are moving faster, but it's the same rate. And if you increase the volume, this one moves slower, and then so does this one moves slower. So the reaction, the equilibrium doesn't shift. Okay, so that's good to know. Okay, cool. Let me show you a tragic and amazing example of this. It's called the Haber process. And let me hide this from you. Okay, all right. So the Haber process, he made an unfortunate reaction possible. NH3 ammonia is the main ingredient for a few things, for fertilizer and for explosives. And during World War II, there was a blockade around Germany, and they couldn't get their source of NH2. Most of their NH2 came from bat crap from Latin America, and they couldn't do it. They couldn't get enough ammonia. See, the only thing that can really do it are the rhizomes, the nitrogen fixing bacteria at the roots of plants. They can actually combine nitrogen in the air and hydrogen to get ammonia that we need for life. But without them, it's a really important reaction if you want NH3, and you can't get plants to do it fast enough for you. So there was a shortage of NH3, so he created the Haber process, named after himself, which he used to make explosives for World War II. Yay, boo! Which led to a huge death, right? But it also led to a huge spike in population. This reaction is probably responsible for billions of people being born because you have more plants, you can support more life, and leading to overpopulation. Or you could say it cancels out. Haber, though, is tricky. He was a German Jew. His parents were Jewish. He converted to Christianity. In World War I, he actually created the first war gas, chlorine, which he used to gas people in the battlefield. He thought it was more humane, but the rest of the world eventually outlawed it for being not humane, so he's kind of a tricky character. His wife actually committed suicide, they say is linked to his refusal to not to give up that work. So it's pretty tragic. Also in World War II, after creating this amazing chemistry, Hitler and company figured out that he was Jewish, and he had to flee the country, and he kind of left. He started out a hero, and he left pretty lost at the end. So, sad story. And also, science can be good or for evil depending on how you do it. I know, right? How do we transition out of that? Well, let's talk about the chemistry, because it's brilliant. Complex people make complex things. So, ammonia, N2 plus 3H2 goes to NH3. The reaction has a very low K. Look, 1.5 times 10 to the negative fourth. That means there's very little product to reactant. So it's tiny, right? We're talking tiny. This reaction does not want to go. Even though it's exothermic, it could be that the hill it has to get, the energy of activation is too high. So how did he do it? So I put this here in heat. How can he drive the reaction that way? Pause it for a second, see if you can figure it out. Okay, welcome back. how did he do it? He did a few things. He increased pressure because there's more particles here, and that drove the reaction this way. He decreased the temperature. He removed the heat from here, so that drove the reaction this way. He also, because it was cold enough, this condensed into a liquid, and he pulled that out, and the liquid doesn't affect equilibrium. So that also drives the reaction. And he did something else, which we'll get into when we talk about rates. He lowered the activation energy by coming up with a catalyst. And that's usually like a metal powder, or that it creates a bed for the two atoms to meet each other really easily, and it makes them bond a little easier together. So that's how we sped the reaction up and pushed it in the right direction. Okay? Great. Speaking of liquid, final thing I forgot to post, note on K. When you write K, only include the substance that changed the reaction when you add or subtract them. So, in a gas reaction, it's only gas. In solution, it's aqueous. If it's not in solution, if you have a big solid or a small solid, it doesn't change the rate that much. It does a little bit, but not that much. So usually leave it out. So say you had a reaction that had this solid plus gas goes to gas. You just, in the K, you just write in the gas amounts. You leave the solids out. And then same thing if you had liquid and aqueous, unless they explicitly say it reacts like that previous reaction, then you just have the equilibrium concentrations here. Okay? That's it.